As we get further in this course, we can actually start to talk about, I would say, some interesting things. This is a picture of water beating up on a lotus leaf. And what it is, it's an area called biomimicry. And it's where scientists try to use things in nature, either by modeling or looking at different systems, in order to solve complex human problems. You've heard of Gore-Tex, the material that is breathable, that keeps you dry. Well, imagine the thought processes that went into that. And that's really what this is about. This chapter is about intermolecular forces. The usual yada, yada, yada. I will let you work through this by yourself. But what I want to do is focus on something. In an older version of Brown-Lemay-Burston, we had what I think were really great pictures. It showed a picture of a gas that had total disorder, and particles have complete freedom of motion, and they really are further apart, but the artist drew them this way. Then it says if I cool these or increase the pressure, what happens is they have less order. The liquid still has disorder, but the particles are free to move relative to each other, and they are getting close together. As I cool them down more, what I will have is a crystalline solid, which is a very ordered arrangement. Particles are in fixed positions and they're very close together. Well, notice I drove this to the right. You could also drive this to the left, where if you add heat, you'll get the liquid. If you add more heat, you'll get the gas. Keep that in mind because we already talked about kinetic energy, how temperature is a measure of kinetic energy. And as we look at species, that's what we see. So this is actually section 1.1 and a little bit more technical than what you might have had in high school. This is called the uncondensed phase, and it is the gas. It's what I showed before, but I like those pictures better. There are weak forces between the molecules, and what we say is the average kinetic energy is less than the energy of attraction. Somehow I prefer those early pictures because here is their picture now of a gas. You've only got two little molecules and somehow you're supposed to read that into it. And it shows chlorine gas. Chlorine gas is yellow. Contrast that to the condensed phases, and there are two of them. One of them is a liquid and one of them is a solid. Think again of the picture that we just had, the old BLB. In a liquid, yes, there are attractive forces. They're strong enough to hold the molecules together, but they're weak enough so molecules will relative to each other. I almost said water because I'm thinking of water in a container, how it can slosh around. But then think about ice. When we have a solid, there are very strong forces that lock molecules in place. They have a fixed position, and they are termed incomprehensible. Well, here I like to think of ice. Here I like to think of water. Here I like to think of steam, all right? And that's hopefully how you can think about it, but think about the kinetic energy versus the energy of attraction. Here, the kinetic energy is less. Here, the energy of attraction is more. So what else do we have here? Well, it's kind of an intro to intermolecular forces. There's a lot of information in section 11.2. So part of it I'm talking about here. There are two types of forces. You already know about what is called the intramolecular forces. They exist within a molecule. So if I look at HCl, that is a covalent bond, and that is an intramolecular force. It is within a molecule. It can range from, say, 100 to 1,000 kilojoules. And think, a nitrogen triple bond is like 937. So again, that's where we get those numbers from. What we want to talk about in this section is intermolecular forces. They are forces that exist between different molecules, and that is like magnetic marbles. If you've ever played with them, you notice the closer they get, they can attract one another. And intermolecular forces are anywhere from 1 to 20 kilojoules. And it's kind of hard to do their definition, but we're going to work with that in 1210. Well, if you see down here, it says weak intermolecular attraction. And what it is that dotted line. These aren't real like lines, but what they are is they're forces of attraction. So there are 4 kinds of intermolecular forces. The first of them is called London. We'll talk more details in the next section. They run about 2 kilojoules, and every single molecule has them. We'll next talk about dipole forces, and that builds on what you already know. That's where you have an ion or you have a polar molecule. So we could have a negative ion or a positive ion, and we talk about polar molecules. We usually use this sort of terminology. We learned about that with Lewis structures. Then there's hydrogen bonding, and you have to have very specific covalent bonds in order to activate a site for hydrogen bonding. Finally, there are ion-ion, and that is going to be something like sodium chloride. All right, that's ions only. So you notice we have an order. I want to tell you something going in right up front. Every molecule has London, but if you have a C and an H, you definitely have London. Molecules that have dipole have oxygen, nitrogen, sulfur, and phosphorus. Molecules that have hydrogen bonding, well, they have those 3 kinds of bonds. Now, this is just not going to change. And the sooner you're able to look at a molecule and recognize the elements and identify the type of bonding, the easier it will be for you to answer the questions in this chapter. So again, 4 different types. Oh, forgot to label the last 2, but there they are, 4 different types. And why are they important? Well, we say intermolecular forces correlate with physical properties. You know, we measure a melting point, we measure a boiling point, but did you realize that it actually correlates to something? So, you know about chemical bonds, ionic, metallic, covalent. Those are the examples, and again, they're very high in terms of their melting points and boiling points. But when we look at the intermolecular forces, these are the 3 we've talked about because the ionics are up here. And notice dispersion forces, something like nitrogen, and look at its melting point and its boiling point. Dipole interactions, they're a little bit stronger, something like HCl. You notice that as we go to a stronger force, the number's going to go up. And then we have hydrogen bonding. That'll be something like hydrogen fluoride or even water. And that's where our melting point and boiling points are really going to increase. So that's the reason for this chapter, so that you can learn the underlying reason for where do physical properties come from. And remember, the lotus leaf, why does water bead up? I mean, we're getting to things that you can actually visualize, and this is the models and the concepts and ideas behind it.